Tilman was able to bring the attention of many well-known stellar archaeologists. So today we are ready to kick off with the first ARENA online seminar for this year by Professor Tilman Hartwig. Tilman, he received his bachelor and master degree from the University of Heidelberg, and he did his PhD in Paris. Also, he did 1 year of postdoctoral work at the University of Tokyo, and then he joined the University of Tokyo as an assistant professor. So his research focuses on like searching in extensive astronomical surveys to better our understanding of how the first stars form and how like artificial intelligence improve the science gained in the stellar archaeology field. I'm really excited to have Tilman here. So he will be telling us about some properties of the first stars, and he will also share some of his recent research, some of the new and most recent results, which are based on theoretical models of the chemical yields of the first supernovae. And so in behalf of the ARENA community, I welcome Tilman to start his talk. Sorry.
Well, thanks a lot, Mohammed, for the nice introduction. Thanks to the organizers for inviting me. And thanks for everyone for joining. As I said, it's so great to see some faces who I haven't seen in a long time. And also thanks for your flexibility. As I understood, usually this talk is a bit earlier, but due to time constraints, I'm now in Tokyo. Here it's 8 a.m. in the morning. So in any case, thanks a lot for joining. So exactly, today I would like to give you a general introduction to how we can use metal-poor stars, old galactic stars to understand more about the first stars. And as I was told, the audience is quite broad and diverse, and there might also be some undergraduate students. So I will also start with a general introduction into the topic. As Mohammed said, one of my research interests are the first stars. And basically, that's kind of my main research interest. And so over the last years, I then started using stellar archaeology and machine learning to better understand the properties of the first stars. And this is also kind of the main focus of this talk. So let me first motivate why I care about the first stars and why I think also you should care about the first stars. So the first stars, they formed in the very early universe when there was only hydrogen and helium. And that's kind of the definition of the first stars, stars that form out of only hydrogen and helium. And these first stars have then produced the first heavier elements. And what is crucial about the first stars is, for example, to understand their initial mass function. So the mass distribution of stellar masses when we sum or average over all first star forming environments. And why this mass function is so important is because the first stars, they will produce feedback like radiative, chemical, or mechanical feedback, but the contribution to these feedback channels depends on the stellar masses. And so understanding the stellar mass function or the average mass of the first stars is important to understand how much they have contributed to the different feedback channels. The problem is we have close to no idea how the first star mass function looks like. And so we only have several indirect constraints that we are trying to use. And some of them I will then introduce in the next few slides. One kind of constraint that we have is numerical simulations. And what you see here is the expected proposed mass range from numerical simulations as a function of the year of publication. And this is from very different groups with different backgrounds, different numerical methods. And so we definitely see some disagreement. And to some extent, we understand where this comes from, like different numerical recipes, different resolution. But two main things that we should maybe observe is we are not sure if there were low mass first stars from the simulation side. Some simulations predict it, but we haven't found such low mass POP3 survivors, because then their lifetime should be long enough that we should be able to see remaining metal-free stars in the Milky Way, and we haven't found those. And on average, what we can see, that's the second takeaway, the first stars are probably more massive than present-day stars. This is because of different cooling channels in the early universe. I will not go down into this direction today, but we think the first stars are more massive and therefore have already died, which also means we cannot observe them directly, but rely on indirect observation methods, such as stellar archaeology. Now, how does it work, and what does stellar archaeology as a time machine to the first stars mean? So this is our rather simplified picture of the evolution of the universe. So we start with the Big Bang, and we are here after around 14 billion years. And well, this is not to scale. So this is like some logarithmic redshift scale. But at the beginning, there was a lot of nothing. There was hydrogen and helium, out of which at some point we formed the first stars. And these first stars, we probably know they are massive and therefore they are already dead. So we can not use them as direct constraint. However, the first stars have produced the first heavy elements, which then got locked up, or out of which then we formed second generation stars. And these, at least some of them, were also low mass. So some of these second generation extremely metal poor stars, they should have survived until the present day. And now the idea of stellar archaeology, one of the ideas is, in our present day Milky Way galaxy, we can observe such old metal poor stars, which we think are second generation stars. We can try to measure their chemical composition, their abundances. And from this, we can, or we hope that we can learn something about the first generation of stars. So that's the very rough general picture. And I know for some of you, you have known and seen this many times. Maybe you even have seen this slide from me, but I guess some of you who are maybe more in the nuclear physics field, I hope this was at least quick reminder of what is our general picture when we talk about stellar archaeology. Now, just a few ingredients that we need to understand when I then later show our data and our new results. So this is a kind of data that we're dealing with. So this is an example from Else Starkenburg. There are probably 100 other examples that I could have used. So this is a spectrum of a metal poor star. And what we see is there are few absorption lines. So there are a few heavier elements like calcium, magnesium, iron. However, by definition, we are looking for metal poor, extremely metal poor stars. So the amount of iron, calcium, magnesium in those stars is very small. So therefore also the absorption features that we are looking for are very small. So kind of by the nature of the problem, it's difficult to analyze these spectrum and to get reliable estimates. And so we need big telescopes, long exposure time, and high resolution spectra. Or in this case, well, the pristine survey, they were a narrowband photometry survey, but then with spectrometric follow-up. The main message here is our type of data are these absorption lines from which we then try to infer the chemical abundance, and it is difficult to measure. And later on, I will also talk about the uncertainties in our study. Now, once we have the chemical composition of a star, what can we do with it? This is a nice paper study by Vinnie Placco. And how to understand these kind of plots is the blue points or light blue are the observations. So these are here carbon or magnesium, aluminum, silicon, the measured abundances. And so this is in the notation element relative to hydrogen, and the brackets mean logarithmic relative to solar. You don't have to worry about the exact definition at the moment. The point is we get the observation, and then having this image of stellar archaeology in mind, if we say that these blue points are a second generation star, that means these elements must have come from probably one supernova explosion that happened before the formation of this star. And what we can do now is we can go through our theoretical templates of supernova explosions. So these are theoretical models where on a computer we let supernovae explode, and we try to measure, or we measure what abundances, what elements would come out of these supernovae. However, there are a few free parameters for such supernova explosions. One is, for example, the progenitor mass. So the stellar progenitor of such a supernova can vary, and with it, the elements that the supernova produces, or the supernova explosion energy can vary. And that will also vary which elements can escape, which elements might fall back onto the compact remnant, the mixing between those. So we have large catalogs of possible supernova templates. And the point is now we try to find this supernova template that can best reproduce the observations. So at this point, it's just a chi-square minimization, or there might be more sophisticated techniques. But that used to be the standard technique, how people had an observation, and we try to fit the one supernova template that best matches the observations. And now there are already a few interesting questions that we can try to answer. For example, this study by Miho Ishigaki, where she used a catalog of around 200 extremely metal-poor stars and did this procedure of finding the progenitor supernova for every of these 200 stars. And then she made a histogram of these progenitor masses. And this, we are very tempted to claim that this could be the POP3 initial mass function. I will say the caveats in 1 minute, but the idea is when we see these second generation stars, and when we then ask by what stellar mass progenitor those second generation stars were enriched, that means there was a star of maybe 25 solar masses somewhere in the early universe that exploded as supernova. And then we can keep track and do a histogram of these progenitor masses. And this is exactly what these colored bars here are showing. And this is quite exciting because it gives us at least the first hint what were, let's say, the typical masses of POP3 stars. But one of the main drawbacks, of course, is that with this method, we can only probe mass ranges in which we expect supernovae to explode, like below 10 solar masses, or at around 100 masses, it's debatable, or we didn't include parent stability supernovae. So this only probes mass ranges where we expect supernovae. But anyway, I hope it shows the power or the information that we have in extremely metal-poor stars and their analysis. Right, also you can ask questions anytime. So I keep an eye on the chat. You can also, I guess, unmute, or maybe Mohamed looks also someone raises their hand. So if there are any questions, please just feel free. Otherwise, I will continue with the transition to my specific research question. So what I have explained so far, there was mostly in these abundance fitting models, the assumption that we have one star and we fit it with one previous supernova. So this is what I wrote here on the left side. Stellar archaeologists assume one enriching supernova per extremely metal-poor star. This has various reasons. One is maybe kind of historical, that, well, that's how we always did it. And also it's maybe just simpler because already fitting one supernova, you have several free parameters, and fitting two supernovae, you would have even more free parameters that you need to constrain with only a few elements observed. However, if we would ask the simulators, and there was a nice meta-study by Hachime Souza a few years ago, where he compared different simulations of population 3 star formation, so first star formation, and he found there is even some analytical scaling law, but basically the takeaway message is we always find multiples of POP3 stars forming together. And this is somewhere in disagreement. On the one side, from simulations, we see that POP3 stars form in multiples. So there are even several dozens of POP3 stars forming at the same time in the same halo. So it is highly likely that also multiple supernovae explode in the same halo. However, our assumption is we only always, most of the time, fit one supernova per extremely metal poor star. And so I and my colleagues, we started to look into this and asked if we can improve. So this is the following scenario. This is kind of the standard scenario. So we have one first star per mini halo, it explodes as supernova, the elements mix, and we form second generation stars that we then would call mono-enriched. However, if we believe the simulations, we might have multiple first stars, and those would explode maybe with different types of supernovae, different progenitor masses, different explosion energies, different mixing fallback parameters. And so they would produce different chemical fingerprints. And then those elements would mix together and we would what we call multi-enriched second generation stars. So where each star would contain the abundance of multiple progenitor supernovae. And our question was, can we distinguish those? Because the information that we have is only the chemical composition of these second generation stars. And can we, by just looking at the chemical composition, distinguish between these scenarios? Because on the one side, it would tell us quite a lot about the star formation properties of the first stars, about the multiplicity, also about the star formation efficiency, which then would tell us something about their feedback efficiency. So we do this with machine learning, and I just have a short interactive part where I need your help. So to understand the basics of machine learning, I'm having this simple example. And the question is, and please use the chat, what do you see in this picture? Maybe some of you have already seen this experiment, but please use the chat to write, and I already see one correct answer. Very good. We see a cat in this picture. Thank you very much. I hope that was not too difficult. Now, what do you see in this picture? Does any one of you know? Again, you can use the chat or you can use the, you can just speak up. Someone knows it. Okay, Erica says antelope, Alex says an anteater, interesting. I was saving the question for you. And it's very interesting because I'm afraid those are not yet the correct answers. However, it is interesting how people directly have an association with it. So although you might have never seen this specific picture before, like an antelope is quite close, like it has some similar features. I guess we agree. Hirora, I have never heard of this, but at least that's not the name that I found for this. Interesting. Something from Star Wars, that's quite close. Evox, yes, it's nice how all of you have associations with this animal, although probably no one has seen it. It's not photoshopped, it's a saiga. So these are some kind of antelope, maybe, that live somewhere around Mongolia and that are close to extinction because their horns are said to have some pharmaceutical impact, whatever, but that's not the main topic here. My main question is, why was it so easy for you to identify the cat as a cat, but so difficult to identify the saiga as a saiga? And I guess that's just my crazy claim that most of you have seen more cats in your life than you have seen saigas. And so kind of your brain is trained to see and identify cats as cats. And what has this to do with machine learning? That is also one of the formal definitions of machine learning. A computer program is said to learn from experience E with respect to some class of tasks T and performance measure P if its performance at tasks in T as measured by P improves with experience E. In non-mathematical words, it means we get better with experience in identifying animals, but also on some classification tasks that we want to do with machine learning. Now, the machine learning technique that I'm going to use is support vector machines. And to give you a rough introduction to these, I have another interactive exercise. And for this, in 1 second, you will need the annotation feature in Zoom. We have already tested it. It should in principle work. Depending on your Zoom version, you either find the annotation feature here at this pan, if you have some touch screen device, it might look like this. Also, don't worry, not everyone needs the annotation feature, but it would be nice if a few people could use it. And the task will be the following. We want to discriminate two classes of data. So for example, we have the orange stars and we have the blue squares in some two-dimensional data plane. And now we want to find a good decision boundary. And now I invite you, everyone who found the annotation feature, please draw a decision boundary between the orange stars and the blue squares that you think is suitable. And great, I see many decision boundaries, probably very good decision boundaries. So far, so easy. So that was just that you can all find the annotation feature. The task will be a bit more tricky in 1 second. Oh, Brad is challenging everyone else, but maybe it's still a good decision boundary. So the first thing that we need to agree on if we have such a classification task is an optimization goal. So what do we want to achieve with our decision boundary? And probably one thing is, well, we want to separate the blue squares from the orange stars. And every line, also Brad's line, is fulfilling this optimization goal. Now let me allow to remove yours for now and give you the next task, which is basically the same. Please again try to draw a decision boundary for this type of data. And our optimization goal is we want to discriminate the blue squares and the orange stars. And perfect. So I think Alex G was one of the first to just draw a straight line and ignored this blue point down there. And later on, I couldn't keep track of the individual people who annotated. But it's interesting that now we have a few people, I would say maybe a third or quarter, who would like to include this blue point here in the decision boundary. And there are, I think, the majority who still just draws a straight line. And, or Jimmy needs a third dimension. Wait for the next slide. Well, I agree, it would be easy in the third dimension. It depends now on the task that we want to do and what misclassifications would mean in practice. But if we just have this, then probably, personally, I would also prefer just a straight line. And that is kind of the idea of regularization, that we try to ignore outliers, because such a decision boundary might look a bit artificial if we forcefully want to include this blue square that is somewhere in the middle of orange stars. Of course, we need to know our data a bit. We need to know exactly what we wanted for at the end. But probably if we use regularization in our machine learning classification, then a straight line would be kind of the more robust, the more generalizable decision boundary. And the last one, let me just get rid of your drawings here. And now in this case, but can you find a decision boundary that is just a straight line in this plane? If you just have a straight line or a plane or something, are you able to separate these orange stars and blue squares from each other? I give you some time, maybe someone has a creative idea. Erica says a straight line and polar coordinates, maybe. That's good. Clustering, yes. So the polar coordinates is already very good. And I saw Jimmy said before she needs a third dimension, and I very much agree. And the fact that nobody annotates something here, I guess, means it is difficult if you just have a straight line to separate the stars and the squares. And here comes the third kind of ingredient for our technique. We can use a so-called kernel. And that's, if you want to, you can think of it as some coordinate transformation into polar coordinates, and then use kind of the radius as a third dimension. Exactly, yes, or folding the paper, so some manifold transformations, and then we can find a decision surface, and then with just one plane, we can discriminate these data. And so these are the ingredients that we also need in our supervised classification. We have an optimization goal. In our case, we want to discriminate mono-enriched from multi-enriched stars. We will have some regularization so that we accept some misclassified outliers. And we use a kernel at the end so that we have some more flexibility in the decision boundary. And you will not need any more annotations anymore, except you have to draw some annotations on my slides. But basically, coming back to stellar archaeology, when we have our data, and I could give an entire talk how we generate the data, because this is really crucial in supervised classification, because the final prediction can only be as reliable as our data that we use. So we use the population 3 supernova yields from the Japanese group, specifically from Miho Ishigaki 2018. And then we generate mono-enriched stars by just taking these values at face value, or multi-enriched stars by combining random pairs of supernova yields. And you can see here the elements in this moment are rather arbitrary: aluminium over manganese and carbon over nickel. What you can see is that the mono-enriched stars, they spread a bit farther, because multi-enriched stars, if you take supernova yields together, it is effectively an average of yields. So therefore, the multi-enriched are some subgroup of the all possible yields that we can get. And now we use support vector machines. I will say on the next slide exactly the math of support vector machines. And we ask them to find a decision boundary. And this is what we would come up with in such a case here. One thing that you have noticed is in 2 dimensions, this problem is very degenerate. So there are regions where there are mono-enriched and multi-enriched stars. However, when we ask then the computer, the machine learning, to learn from experience and find kind of a probabilistic region in which it is more likely to find multi-enriched or mono-enriched stars. And so this is then what we do. I show here only in 2 dimensions because our human brain prefers 2 dimensions. Later we do this classification in 4 dimensions. So you can imagine this as some 4-dimensional hyperplane surface. A quick note on support vector machines. That's maybe not the main topic of the talk, but still, so that the machine learning does not remain black magic. It is a very simple idea. If we have our simple optimization goal, and if we have linearly separable data, like in this example, what we're trying to do is, well, we try to find some plane that separates the stars from the squares. However, we try to find a large margin, and this is also known as the large margin classifier. So this distance between our decision surface and each side of the classification, we try to maximize it. And this is an iterative learning process. And this is in the case where we have linearly separable data. In our degenerate case, what we try to do is we try to, well, minimize the outliers, and by how much, like by how much orange star would be on that side of the boundary. And so we have an optimization goal, and then again, we use radial basis function kernels, and we use some amount of regularization so that our decision boundary is not some weird zigzag line. And what we get out is this. Again, this is just a 2-dimensional representation. And we do not only train one support vector machine, but we train here 8 different support vector machines, and actually in 4 dimensions. The 2-dimension is just for visualization. Why do we use 8 support vector machines and not just 1? The reason is, well, there are three reasons. On the one side, it allows us to include different elemental abundances. So if we just would have like 2 dimensions, we could have maybe 3 or 4 different abundance ratios. But for some stars, we have more abundance ratios observed. So we kind of want to make use of all the possible abundance ratios that we have. Also, it mitigates overfitting, because if we just have one support vector machine, as we saw in one of the examples, some of the decision boundaries might try to overfit the data, so kind of to memorize the individual data, which is not good. Instead, if we have different support vector machines that might have somewhat different opinions, we can then let them vote and have a majority vote or a weighted majority vote on the final classification. And it is robust against missing data. And that brings me back to my introduction, because it is in principle difficult to observe elements for extremely metal-poor stars. And not for every star, all the elements are observed. And so if for one star that we at the end want to classify, one real observed star that we want to classify, if an element is missing, but we only have one support vector machine that relies on this element, we couldn't classify the star at all. However, if we have different support vector machines, different classifiers that rely on different composition of the elements or different subgroups, subsets of the elements, then even if we cannot use a few of those classifiers because of missing elements, we can still use a sum of them. So sorry, that was a long story to make you understand why this ensemble learning of combining several classifiers together is more robust in our case. And now I've been already talking 30 minutes. So we come to the results. And this is just a very quick justification. And I will not tell you too much because it's a boring theoretical slide. It's just saying that we tried our best, and at the end, we achieve a classification accuracy of like 66.7%, which is not amazing. However, you have seen how degenerate the classification is. And so we think this is already a big step in the right direction. And I will try to convince you later that we still think at least part of our classification are quite reliable. And so, right, I will not go into detail here. If you want to know more about the machine learning and the training and the validation, you can please ask me later. And this is one of the main results. So what we do in machine learning, we first have our training data, in which we assume that 50% are mono-enriched and 50% are multi-enriched. Then we have blind test data. So data that we kept secret until the very last moment of our classification task, so that the computer has not yet seen to base any decision on. And if we then let this test data be classified by our trained classifier, we get very much 50%, 50% back. So we think we have a very unbiased classifier. If, however, at the end we look at observations and we have a compilation of over 400 EMP stars, if we let them classify, then we find that the majority of them is classified as multi-enriched, and only like 1/3 is classified as mono-enriched. And this is already quite interesting. And now we can look further into the trends of this classification. For example, what we see here are, maybe in the top panel first, these are our individual stars that we have classified as a function of metallicity. And it goes from -6 to -3. So we included extremely metal-poor stars. And here you see the probability of mono-enrichment. And the kind of the boundary would be at 50%. And you can see that some of them, especially at the lowest metallicity, are rather mono-enriched. At the bottom, we basically see the fraction of mono-enrichment. So it's basically this top panel, but kind of in bins, we check what is the fraction of mono-enrichment. And what we see here is a quite interesting trend, that at the lowest metallicities, basically 100% of the EMP stars or hyper or ultra metal poor stars, they are mono-enriched, so enriched by only one progenitor supernova. At lower metallicities, at higher metallicities, but still -3 is extreme metal poor, the majority seems to be multi-enriched. And this is quite interesting and a quite almost natural trend, because simply to be multi-enriched, well, you need at least 2 supernovae, which provide, on absolute terms, more metals. So it makes sense that we find multi-enriched stars rather at higher metallicities. However, please keep in mind that it is a very degenerate classification problem. And so what we present here, we would rather interpret these as trends, saying maybe for this star, it is more likely that it is mono-enriched. However, with our method, it's very difficult to make absolute statements. Also, you can see the general prediction range is like between 25 and 75%. So we have almost never the case that we are 100% sure it must be one or the other. And well, this has various reasons. Some of them are rather technical. So if you want to know more about it, again, you can ask me later in the questions. One super interesting result that we found, oh, sorry, I have to mention one more thing, which is super exciting about the data that I forgot to mention, because we see a quite clear trend with metallicity. Metallicity meaning iron over hydrogen. However, in our training, we have only used relative abundance ratios of one element to the other. We have not used the absolute metallicity in the training. So this trend with metallicity is kind of achieved agnostically. Like, we do not use the absolute metallicity information, and still just from the relative abundance ratios, we can recover such a trend with metallicity. And this is quite, well, comforting or reassuring that our model actually learns some physics. Now, coming to some of the interpretations that we can obtain from our model. So in this representation, we see carbon over hydrogen and iron over hydrogen. So the carbonicity versus the metallicity. And this dotted line shows the conventional threshold for carbon-enhanced metal-poor stars. I will not go into details what they are. At low metallicities, we just see some stars are carbon-enhanced. Several people in the audience have worked on this for quite some time. And now we can color code these stars. So the points are our EMP stars that we have analyzed and classified. And if we color code them with what we find the probability of mono-enrichment, we again see a quite interesting trend that almost all carbon-enhanced metal-poor stars are mono-enriched. And this again is quite interesting because we did not use this as a constraint or anything. Our model knows about carbon over iron or something, but we didn't force it to reproduce this trend. And also this line of carbon over iron greater than 0.7, it's some empirical human-made boundary, but it seems to quite well separate the stars into mono-enriched and multi-enriched. So again, we wouldn't trust too much the individual stars. However, it's again nice and reassuring that the results have some physical meaning and allow some reasonable interpretation. And one last kind of result discussion is, what can we now learn from this? Beside the impact on the first star formation, that it probably means most first stars have formed in multiples, although at the moment we're a bit careful with this direct interpretation. A more interesting and a more reliable interpretation is the information importance that we get from different elements. So as you have seen before, we have used various elements to train our support vector machines. And now we can ask, how important is each individual element in the classification? And for this, we use the permutation feature importance. Again, because of time, I will not discuss it in detail now. If you want to know more about it, ask me later. But basically, we can then rank the elements according to their feature importance. And here you see, for example, from silicon to oxygen, I have to admit that the scaling is a bit skewed. So it just goes from like 61 to 66%. But in any case, we see some relative importance. And what this number means is, well, I will not give you the exact mathematical definition, but basically what it means is oxygen is more helpful in discriminating mono-enriched from multi-enriched EMP stars. And this, I hope, will be helpful to guide observers in the future, or to get them more observation time, to get more better, deeper observations of oxygen, for example, because this seems to be a very helpful element for us in discriminating mono-enriched from multi-enriched stars. And that's everything that I wanted to tell you today. So let me summarize. I presented in a more general context how we can use stellar archaeology, so old metal-poor stars in the Milky Way, as a time machine to the first stars. So to better understand the properties of the first stars, which otherwise we have almost no handle on. And I introduced support vector machines as a very versatile, flexible machine learning technique that can be used to classify astronomical data. In our case, it can be used to discriminate mono-enriched from multi-enriched second-generation stars. And we saw the different ingredients of our support vector machines. We would like to claim the first observational confirmation of the multiplicity of the first stars. However, we are still questioning also ourselves how reliable this quite strong conclusion is. So we definitely see a tendency for this. And we can, with our machine learning method, identify the feature importance, so this percentage, how important are the individual elements in making this classification, and we hope that we can use this to optimize upcoming surveys. And that is my talk. Thank you very much for your participation and your interest. Thanks a lot.
Thank you so much, Tilman, for this great talk. So I see that Alex raised his hand.
Hi, Tilman, how are you doing? That was a really fantastic talk. Thank you.
Thanks, Alex.
I have a question about sort of the underlying prior from the theoretical models, especially relating to the sort of mono-enriched fraction as a function of metallicity. So the models that we've developed for the supernova yield calculations, especially trying to get things carbon enhanced, have been strongly influenced by the fact that we are we use these observations at the low metallicities to influence that. So I'm wondering, like, how much of a sort of implicit prior is there in sort of producing this when you generate sort of the training sets? And sort of another way of asking that is, if you, instead of metallicity, iron over hydrogen here, you converted it to like total metals, including the total amount of carbon, how would that look?
That's an interesting test. We will definitely do this. Thanks for the suggestion to use absolute metallicity. So I just don't know. About the prior bias that we might have included in the data, and I didn't probably explain this in detail, because you're completely right. This is a very serious problem, because as I said, the final prediction is only as good as our training data is realistic. And if our training data would be biased by previous stellar archaeologists needing some crazy exotic supernova yields to explain their observations, the data would be biased. So how we generated the training data is, I say here we use the yields from Miho Ishigaki. However, we don't use all the yields, because these catalogs, these are huge and allow for rather crazy parameter combinations where we can then get carbon over iron of 10 or something like logarithmic. So we took a subset of supernovae that are already able to reproduce existing observations. And if you want to know, I can give you the entire details. It is a quite, well, iterative, delicate process with also several assumptions, but we think the supernova set that we use as start of our training is realistic in the sense that it is able to reproduce already the existing observations. So we don't exclude any exotic or crazy high carbon enhanced supernovae. However, then there are, of course, further prior constraints, like that we assume a fraction of 50%, 50%. But we have tested that this is rather robust. So I don't know if this had completely answered your question, but at least we are aware of these problems and we have tried to mitigate them and do some additional tests. And I will keep in mind to plot the fraction as absolute metallicity as you suggested.
Great, thank you.
Okay, another question from Tim.
Yeah, just a comment. First, I really appreciate the direction that you're going with this. I think it's necessary, in particular for someone who has no axe to grind, right? You have, you're trying to look at the data as it exists and interpret it in a fair manner, which is difficult to do if you are finding the data yourself. But, excuse me, along those lines, I think it sort of touches on Alex's question. How you select observational samples potentially has a huge impact on interpretation. And that's going to worry among the spectroscopic community for decades. But we're now at a point, which I'm sure you're at least reasonably aware of, we're now at a point where we actually have techniques to identify stars even at these low metallicities photometrically. You've highlighted Pristine, but of course SkyMapper, and there are other surveys. One which some of you might have heard of called SAGE from the Chinese, which have a narrowband filter on the calcium K region. And there are others, S+, J+, et cetera. So we're entering a new generation where we don't have the difficulty of selecting which stars should be followed up, which is invariably a limitation, right? That's a spectroscopic selection. We can begin to look at stars or select stars solely based on photometric information. And the advantage, of course, there is that we don't really have to model the selection function. And so in the past, we didn't even bother to model it, we just ignored it, right? And we hoped for the best. We have reasons to justify that hope, but so what I see as interesting here, among many things, is that these new generation photometric surveys have huge numbers. The numbers are large, even in the context of other large numbers. So there is a soon-to-be published version of the recalibrated SkyMapper data, which has 500,000 stars below -2, of which 25,000, according to the photometry, are below -3. And so I would argue that a natural step forward is to think about campaigns which are photometrically selected in this, in this way, and obtain a more fair representation of what the universe, at least in the context of the galactic stars, actually looks like. And I think that is in great part motivated by what you're trying to do. And I appreciate the fact that the not including the metallicity, that's a very important step in your argument, because it's agnostic and it's just looking at ratios. The fact that the CEMP stars showed up so clearly separable is obviously telling us something. So I actually do have a question. Have you gone to the point of looking into the data and taking out stars that are demonstrably binaries among the CEMP stars? That would be an interesting question.
Good point. Also, to first explain something before I come back to your question, we do only classify based on elements up to zinc. So we do not have barium or higher elements. However, sure, for some observed stars, we have this information. And so we can then check what is the probability of mono-enrichment as a function of barium, for example, or as a function of binarity, or just checking the two groups. We did not find a strong trend there. So, but that in the case of binaries, or when you think about barium, that kind of makes sense because we don't train on barium, so our model is rather agnostic to barium.
Right, right. Well, okay, I think that's interesting because previous work going back 20 years shows that, of course, there are what are presumably AGB mass transfer episodes, even at -3 or below, but they're quite infrequent. That is, it's not that they can't happen. It's that it's just not a favored way of building up significant amounts of carbon. Because that carbon, of course, at least if it's in a binary, it's trapped, right? So you worry about the ones that don't have a binary you don't ever see. But if you have very few binaries that trap them, then you might extrapolate to say, well, of course, we don't know exactly what the binary fractions do at low metallicity. On the other hand, it gives you more confidence that the binary impact on this argument is less at low metallicity.
I think the binary fraction is also a nice transition to Brad's question that I see in the chat, but let me first comment on Tim's comment also, which is, I'm very much looking forward to more data here because, well, machine learning, we are data driven and more data will improve our estimate. And especially, as you correctly said, it depends on our selection of EMP stars. And the 400 EMP stars, the sample is very heterogeneous and we try to homogenize it as much as possible. But of course, the underlying question for the interpretation is how representative are those 400 selected stars for the general population? And so, right, I could tell more about how we did it, but that's maybe getting a bit too technical. So may I rather answer Brad's question?
Okay, go ahead, thanks.
Yeah, so Brad is wondering how robust these findings are when you are considering more resources of enrichment and the few that you mentioned.
No, exactly. Hi, Brad, and thanks, Brad, for the question. So one thing that I also didn't explicitly mention because of limited time is, well, mono-enriched is, so first things first, we only consider population 3 core collapse supernovae. And I will comment on other enrichment channels later, but the mono-enriched here is one supernova. The multi-enriched actually contains multi-enrichment by 2, 3, 4, and 5 supernovae. So we did some tests if this matters in one direction and the other, and we found if we take this range 2 to 5, the results are most robust. So in that sense, we also include enrichment from more than one supernovae. However, it still remains population 3 core collapse supernovae. We didn't include pair instability supernovae because in the data so far, we haven't seen a convincing feature of pair instability enrichment yet. And we didn't include any R process or S process sources explicitly because already this problem is degenerate enough to be discriminated. And so what we did, and that was exactly our cut in metallicity, why we focused on extremely metal poor stars, because there we can be quite sure that population 3 core collapse supernovae are the dominant enrichment source. There might be other contributions, but at least we are dominated by the POP3 core collapse supernova signature. However, if we have more data and more time, it would of course be super interesting to extend this either to slightly higher metallicities or with somewhat other enrichment channels. And so we're open for any suggestions, or if someone has nice data that we can use as training data, we're also very happy to collaborate.
So Tilman, I have a kind of follow-up question
Please.
Regarding this binary stars or core collapse supernovae. So in your sample here, yeah, this one or the other one, the previous slides, the top panel stars are plotted here, right? On this, is that right?
Exactly right. These are our like 400 EMP stars that we plot here and that we plot here.
Yeah. So you mentioned that you only consider the stars would potentially explode as a core collapse supernovae, right? but we know that below -3, I mean, as the team mentioned, there are some binary stars, and not only binary, but even if they are single stars, there are some high barium stars, right? Especially, I see that the C/H0 is like solar carbon, which means it's super high. And I don't know if it's really possible they could be a mono, and then they might likely to be some CMP S star rather than just a CMP no or something. So when you do this analysis, did you exclude them?
Thank you so much, Jimmy, for your question. That's an excellent question, and it's something that we have also worried about. Because as I just said, right, we only assume core collapse supernovae, also faint, but if then a star would be enriched by something else, then our classification would be completely wrong, because it's, right, basically kind of like the Saiga example, because then you have to classify something that you have never seen before, that you were not trained to classify. And so what we did as some test at the end was, I was looking if I have the slide as backup, but unfortunately I don't, where we plotted was it just barium over hydrogen or barium over iron versus the P mono fraction. And what we found is our classification is at least agnostic to the barium fraction. So it's not like that it classifies barium enriched stars preferentially as one or the other. So in that sense, at least I hope we're not biased. And the problem in the other direction was, we also were thinking if we should exclude stars that are highly enriched in S process or R process. But then the question would also be, where do we put the boundary? At what value do we consider something to be S process or R process enriched? Because if we put the boundary too low, then we would lose stars that are maybe actually enriched by co-collapse. So it's a tricky question, but what we have done in tests, what we looked at least we found that binary stars or S process enhanced stars, they do not bias the final mono to multi fraction.
Okay.
Yeah, so I can see that Alex is raising his hand, and perhaps this is the last question. If you have any other questions, you could join Tilman in the Gather Town.
Sorry to keep asking questions. Tilman, I'm wondering, so I was very interested in the sort of importance of different elements. And I guess what I'm wondering is it possible, can you like define a minimum set of elements that we need to do this classification that you've done? In some sense, that's, you know, we can try and get other elements, but there's also, in terms of trying to get the maximum number of stars, you might be able to get more stars with like fewer elements, right? If by taking resolution hits or something. And I guess it may be also similar to that, as you change the number of, I know you sort of did an ensemble method, but as you change sort of the maximum amount of information available globally, does it actually improve or unimprove the ability to tell the difference between sort of the single and mono enriched stars?
Thanks. That's an excellent question, and I see the kind of difference between our brain sets. For me, it was the theoretical observation agnostic physicist who said, "Hey, here you have the information importance for oxygen. No, go observe more oxygen, please." But of course, your question is more practical. So yeah, what would be the minimal set that we actually need to observe? And I do not have the question right now, but it would be an interesting question that we can answer with the data that we have. Like, what would be the minimal set of a handful of elements that we definitely need to have observed together to confidently classify into mono-enriched and multi-enriched. For the training or the set, or maybe, wait, this slide is a bit better, like the different combinations that we use, and if I understood the question correctly, like if we take more or less elements, if it improves or not. One problem here from the construction of our ensemble learning technique is, and sorry, maybe I have to go back to this. Oh, sorry, let me first stay here for 1 second. So as I said, what we do at the end, we have like 8 different support vector machines that vote on the final classification. And some say it's mono-enriched and others say it's multi-enriched. However, the problem is degenerate. So therefore, we at the end have some kind of central limit theorem that if we just average over many rather undecided classifiers, we end up around 50%, and we don't have any strong classifications towards 0 or 100%. So that's the one side. Like if we take more elements and construct more support vector machines, then we might improve the accuracy of the overall classification a bit, but we just get predictions that are around 50% because it's just some average over undecided classifiers. So, right, there are more things to question or to experiment or to talk about, but it is, right. Let me maybe end with this. So we have tried a lot of different things, and we started with really millions of random combinations for the support vector machines. And this was kind of the optimal set that we could come up with, if that answers the question. And I see that.
Rana, perhaps you would ask again your question to Tilman in the Gather Town. So thank you, Tilman, again for this wonderful talk. And we want just to remind the audience that we will meet again on the 4th of February, and the speaker will be Dade Kao. So thank you again, and see you in 2 weeks.
Thank you very much for coming, and thanks for your questions and interactive participation. And right, as I understand now, we meet also on Gather Town for those who want, right?